Module 1, Lecture C, Data Thinking. By the end of this lecture, you will be able to identify tabular, time series, and image-style data structures in civil engineering contexts, explain how features, targets, rows, columns, and samples relate to engineering measurements, and recognize common data quality issues that can mislead models. Civil data modalities. Tabular data. In civil engineering, tabular data organizes information into rows and columns, much like a spreadsheet. Each row represents an observation, such as a road segment or concrete test, while columns describe its properties, such as length, age, traffic volume, curing time, or strength. This structure makes it easier to compare, sort, and prepare data for analysis or machine learning. In civil engineering, tabular data comes from sources such as inspections, lab tests, design records, and monitoring systems. Each row usually represents an observation, such as a bridge, soil sample, catchment, or pipe, with columns describing key properties. Across different subfields, tables provide a structured way to organize information for systematic analysis. Engineers need to recognize tabular data because it shapes what questions can be answered and how analysis should be prepared. Tables can connect measured characteristics to outcomes, such as costs or failures, but they may also hide important variation behind a single row. Each column may represent a different kind of data, so it must be interpreted carefully. Overall, tables should be treated as structured views of real-world conditions and decisions. Python code, tabular data. Civil tables organize engineering observations by placing each sample or asset in a row and each measured engineering property in a column. We begin by importing pandas, a Python library for working with tabular data. It provides data frames that make it easier to organize, validate, summarize, and analyze pavement condition records. We begin by creating a small structured dataset of pavement conditions. Each road segment is represented with attributes such as its identifier, length, age, traffic volume, distress rating, and maintenance need. This format organizes the data so it can later be converted into a table for easier analysis. We convert the records into a pandas table by creating a data frame from the list. Each dictionary becomes one row, with its keys used as column names and its values placed in the matching cells. This makes the data easier to organize, manipulate, and analyze with pandas. The dataset uses a segment identifier to uniquely label each road segment. Its main features describe each segment's length, age, traffic volume, and distress rating. The target is the maintenance need, which is the outcome to analyze or predict from those features. We validate the data frame by first defining the expected column order, including the identifier, features, and target. Assertions then confirm that the actual columns match this structure and that the data frame has 3 rows and 6 columns. These checks help catch structural problems early and support reliable analysis. This output gives a quick overview of a pavement segment dataset. It reports the number of road segments and recorded properties, identifies the feature columns used for analysis and the target column of interest, and then shows the first 2 records to preview the data structure and contents. This script builds a small pandas dataset for pavement condition analysis. It includes 3 road segments with details such as length, age, traffic volume, distress rating, and maintenance need. The data is stored in a data frame, checked for the expected size, and then summarized by reporting its dimensions, key columns, and the first 2 records. Time series data. Time series data is important in civil engineering because it shows how infrastructure measurements change over time. Sensors may record values such as bridge strain or rainfall at regular intervals, and the order of those timestamps is essential. Keeping the sequence intact helps engineers spot trends, sudden changes, and anomalies, making it useful for monitoring and forecasting infrastructure behavior. Time series data in civil engineering shows how observations are connected over time, revealing patterns in processes like traffic, river levels, and structural vibrations. These patterns depend on timing, frequency, and sequence, so engineers must choose data collection intervals carefully. Measurements taken too infrequently can miss rapid changes, while short records may fail to reveal long-term trends. Time series data comes from sources such as sensors, inspections, and control systems, and it records how conditions change over time. In engineering settings, it can track building performance, construction activity, or pavement condition. Treating these records as time series helps engineers study trends, detect anomalies, and account for data quality issues such as missing timestamps or sensor drift. Python code, time series data. Time series data keeps engineering measurements in their original order, making it easier to understand how conditions change over time. Timestamps reveal trends and sudden shifts, while small sensor examples help build practical thinking about civil engineering data. We begin by importing pandas for working with structured data, especially time series, and Matplotlib's plotting tools for creating visualizations. Together, these libraries provide the basic tools needed to manage, analyze, and display time series data effectively. We create a series of timestamps to model data collected every 2 hours across one day. Using a pandas date range, the sequence starts at midnight on January 1st, 2026, and includes 12 total time points. A list is used to store 12 bridge strain readings measured in microstrain. Each value represents a measurement taken at a different time, allowing changes in bridge deformation to be tracked over the monitoring period. This helps assess structural integrity and detect possible issues. A pandas data frame is used to organize the time series data with timestamps and matching strain measurements in microstrain. This format makes it easier to analyze and visualize how strain changes over time. Set the expected row count to 12, matching the 12 hourly timestamps created earlier. Then check that the data frame has exactly that many rows. This simple assertion helps confirm the data is complete and catches unexpected changes during processing. To compare ordered and shuffled data, shuffle the data frame rows using the sample method while keeping all rows. A fixed random state makes the shuffle reproducible, so the order is the same each time the code runs. Afterward, reset the index and discard the old one to give the shuffled data frame a clean, sequential index. We print a brief summary to understand the dataset. Each row is a time-based sample, with columns for the timestamp and bridge strain measurement. We compare the first timestamp in the ordered and shuffled data to show how the order changed, then report the maximum recorded strain in microstrain to identify the peak value. We create a time series plot of strain measurements using timestamps on the horizontal axis and strain values on the vertical axis. Setting the figure size controls the plot's dimensions, while markers make individual readings easier to distinguish. This visualization helps reveal trends and patterns in the strain data over the monitoring period. The plot is formatted to clearly show a bridge strain gauge time series. It uses a descriptive title, labels time on the horizontal axis, and shows strain in microstrain on the vertical axis. The timestamp labels are rotated slightly to make them easier to read when they are close together. The code improves the plot layout so labels and elements do not overlap, making the visualization easier to read. It then displays the plot, allowing learners to examine the time series data visually. This script builds a one-day time series of bridge strain measurements taken every 2 hours, pairing timestamps with microstrain readings in a data frame. It checks that the dataset has the expected number of rows, then shuffles the records to show why time order matters in time series analysis. It reports basic insights, including the first timestamp before and after shuffling, and the maximum strain value, then plots the ordered data to show how strain changes over the day for civil engineering assessment. Image data. In civil engineering, images are data made of pixels that record brightness, color, and location. Because pixels are arranged across space, images of structures or construction sites can reveal physical features such as cracks, defects, or lane markings. This makes image data useful for finding visual patterns that are difficult to capture in spreadsheets. In civil engineering, images provide important data about infrastructure conditions that other methods may miss. Photos, vehicle cameras, and drones can document damage, pavement, signs, construction progress, and storm impacts. Experts in computational models analyze these images by using their spatial patterns to detect features such as cracks or missing materials and assess overall condition. Image style data includes more than standard color photos. Grayscale, thermal, multispectral, and three-dimensional point cloud data can reveal internal features, temperature patterns, environmental conditions, and surface geometry. To use these sources effectively, consider what each image represents, how it was captured, its scale, and the engineering question it is meant to answer. Python code. Image data. Image data stores spatial engineering measurements, with pixels representing visible surface conditions. Small arrays can be used to explain the basic structure of an image. We import NumPy to work with numerical arrays and mathematical operations, and Matplotlib pyplot to create visualizations in Python. Together, these libraries provide the basic tools for handling data and displaying it clearly. The image is set up as a small 12 by 12 grid representing pavement. It is filled with the value 180 to create a medium gray tone, and integer values are used because image pixels are typically stored as whole numbers. A dark diagonal crack is added to the pavement image by changing selected pixels along a diagonal path. The main crack pixels are set to a low intensity, while the neighboring pixels to the right are set slightly brighter to create a subtle gradient and make the crack look more realistic. This code simulates a repaired pavement patch by changing a small section of the image array. It updates rows 7 through 9 and columns 2 through 4 to a brightness value of 225, making that area appear brighter than the surrounding pavement. We validate the pavement image data by checking that its dimensions match the expected image size and that it is two-dimensional. This confirms it represents a grayscale image with rows and columns. These checks help catch data errors before any further processing or visualization. The code summarizes a grayscale pavement inspection image by reporting its type, pixel dimensions, and intensity range. These values help describe the image size and contrast. It also notes that darker pixels may indicate cracks or shadows, while brighter pixels may correspond to repairs or pavement markings. A new plot is created at a manageable size, Then the pavement data is displayed as a grayscale image using Matplotlib's image display function. The color scale is set from 0 to 255, matching the full range of 8-bit pixel intensities. This makes intensity differences visible, helping reveal pavement features such as cracks and patches. The plot is titled to identify the image as a tiny pavement surface example. The horizontal axis is labeled as pixel columns across the pavement, and the vertical axis as pixel rows along the pavement. Together, these labels clarify the image's spatial orientation. A color bar is added to the plot to show how grayscale shades relate to pixel brightness values. Labeled as brightness intensity, it helps clarify the range and meaning of the image's intensity levels. The code uses Matplotlib's tight layout feature to prevent plot elements from overlapping, then displays the finished pavement image with its annotations and color mapping. This script uses NumPy to create a small 12 by 12 grayscale image of a pavement surface. It starts with medium grain pixels, adds a dark diagonal crack, and includes a brighter repaired patch by changing selected pixel intensities. It then reports the image size and intensity range, and uses Matplotlib to display the result with a grayscale color scale, showing how pixel values can represent pavement conditions. Features and targets, rows as samples. In a data table, each row usually represents one sample or observation, such as a concrete test, bridge inspection, or traffic interval. The row gathers all known information about that case, making it possible to compare repeated observations across the dataset. Thinking of rows as samples helps clarify what the dataset is measuring and what its basic unit of analysis is. What counts as a sample depends on the engineering question and how the data was collected. In a bridge dataset, a row might represent a bridge, an inspection, a component, or a sensor time window, depending on whether the goal is comparison, deterioration tracking, or vibration detection. Defining rows carefully matters because overly broad samples can hide important variation, while overly narrow samples can create dependent or repetitive data. Treating each row as a sample helps prevent mistakes in interpreting engineering data. Many rows do not always mean broad or independent evidence, especially when readings come from the same structure or from nearby locations with shared conditions. Clearly describing what one row represents, such as one test or inspection, makes the data structure clearer and supports better decisions about how findings apply to new situations. Python code, rows as samples. In an engineering data table, each row represents a measured sample, while the columns contain its features and target values. Small tables are useful because they make this structure easy to see and understand. We begin by importing pandas, a Python library for working with structured table data. In this script, pandas is used to create and manage a data frame for concrete sample data, making it easier to filter, select columns, and summarize the information. We organize the concrete cylinder data as a list of dictionaries, with each dictionary representing one sample. Each sample stores its identifier, age in days, water-to-cement ratio, and measured strength in megapascals. This format makes the data easy to convert into a pandas data frame for later analysis. We convert the list of dictionaries for concrete cylinder samples into a pandas data frame. This turns the data into a table, with each sample as a row and each dictionary key as a column. In this format, the data is easier to analyze and manipulate with pandas. The data is split into inputs and an output for analysis. The input features are age in days and water to cement ratio, while the target is strength in megapascals. This separation makes it clear which variables are used to predict or study the outcome. Count the rows in the data frame to find the total number of samples. Then check that this count matches the number of target values. This confirms that every sample has a corresponding target and helps ensure the data is consistent. We begin by summarizing the dataset. Each row represents one tested concrete cylinder, and the total row count gives the number of samples. The feature columns describe each sample, including values like age in days and water to cement ratio. The target column is the outcome to predict, which is concrete strength in megapascals. We then introduce the first sample in plain language before describing its attributes in more detail. The first row of the data frame is selected using the iLock method to examine the first concrete cylinder sample. A short plain language message is then created and printed, summarizing its sample ID, age, water to cement ratio, and strength in megapascals. The script builds a small pandas dataset of concrete cylinder samples, using age and water to cement ratio as features and compressive strength as the target. It separates the input features from the target values and checks that their row counts match to confirm the data is consistent. It then prints a brief summary of the columns and describes the first sample in plain language. Columns as features. In engineering data tables, features are the columns that describe each sample in a consistent way. They can be measurements, such as strength or moisture, or categories, such as pavement type or construction method. By recording the same kinds of information for each sample, features make comparisons and predictions possible. Feature columns are meaningful only when their definitions are clear. A value like temperature depends on its unit, where it was measured, and whether it represents an instant reading or an average. Similarly, rainfall over different time periods or separate measures like vibration frequency and wind speed describe different conditions. Well-defined features are therefore engineering variables with specific units and methods, not just column labels. Engineering datasets can be improved by creating useful features from raw data, such as deriving pipe age from installation information or turning pavement rut depth into indicators of deterioration. Similar transformations can support geotechnical analysis with features like soil classification or water content. The key is to choose features that are relevant, accurate, and meaningful for the specific engineering problem, so they clarify rather than confuse the analysis. Python code, columns as features. In a civil engineering dataset, columns can describe measured engineering features, rows can represent comparable samples, and targets are the outcomes we want to explain. We begin by importing pandas, a key Python library for working with tabular data. It provides data frames which make it easier to organize, analyze, and manipulate datasets efficiently. We create a small bridge inspection dataset using a dictionary where each column name maps to its data values. One column stores unique bridge identifiers, and another stores each bridge's age in years as a numerical feature that may relate to other inspection outcomes. The data describes several bridge features: span length in feet, deck condition ratings, and daily traffic volume in vehicles. These values are organized into a dictionary and then converted into a data frame for analyzing bridge conditions. The code stores bridge information in a dictionary with two lists, one for each bridge's material, such as steel or concrete, and one for whether it needs repair. Together, these lists link each bridge to its construction type and maintenance status, making the data useful for analysis or modeling. We convert the bridge data dictionary into a pandas data frame, turning it into a table where dictionary keys become column names and the stored lists become rows. This tabular format makes the data easier to work with and analyze using pandas tools. We define a set of feature columns to identify the data frame fields used as inputs for the analysis. These include bridge age, span length, and deck rating. This separates the predictor information from the target column, which is the outcome we want to predict or explain. The feature list adds daily traffic volume and bridge material type as inputs for predicting repair needs. Traffic volume is a numerical measure that may affect bridge condition, while material type identifies whether the bridge is steel or concrete, which can influence durability and maintenance. The data is prepared by separating the input features from the target outcome. The selected feature columns form a new dataset for analysis, while the repair status column is kept as the value to predict or explain. This clear split between inputs and output makes the data ready for modeling or further analysis. Before analysis or modeling, verify that the feature data, target values, and original dataset all contain the same number of samples. These checks help ensure every input row has a matching outcome and that the data remains consistent and reliable. This overview checks the dataset by first reporting how many samples it contains, then identifying the feature columns used as inputs and the target column used as the outcome. It also shows the first sample's feature values and its matching target value, giving a quick example of how one data point connects inputs to output. The code emphasizes checking what each data feature means before analysis. It notes that bridge span is measured in feet, deck rating describes bridge condition, and material type is categorical rather than numeric. It also confirms that each feature column is used consistently across all samples, supporting reliable interpretation. This script shows how to prepare bridge inspection data in pandas for analysis or modeling. It builds a table of bridge samples with features such as age, span length, deck rating, traffic, and material type, along with a target indicating whether repair is needed. The code separates the features from the target, checks that their sample counts match, and prints a brief summary of the dataset. It also highlights the need for consistent units and clear definitions, especially for numeric measures and categorical fields. Targets. In civil engineering models, the target is the main outcome being predicted or explained, while features are the input data used to support that prediction. Examples include predicting concrete strength from mix and curing data, travel time from traffic and weather data, or maintenance needs from structural monitoring data. Defining the target clearly is essential because it determines the purpose of the dataset and the goal of the analysis. In engineering models, the target is what the model is meant to predict. It may be a continuous value, such as pavement roughness or bridge displacement, a category, such as pipe condition, or a future event, such as flooding during a storm. The target must match the engineering decision, or the model may seem accurate but fail to be useful in practice. Targets in a dataset must be clearly defined, measured consistently, and matched to the correct time for each row of data. Using information from the future or linking a target to the wrong event can make a model misleading. Targets may also contain uncertainty from instruments or human judgment, so these limits should be considered when interpreting results. A target is not just a column. It represents a real-world outcome that needs careful measurement. Python code targets. Targets are the outcomes engineers want to estimate, while features are the measurements available before a decision is made. Each row represents one sample and links its features to the corresponding target. The code starts by importing pandas, a library used to work with small tabular datasets. Here, pandas will help create and manage a structured dataset containing measurements from concrete testing. We create a small test dataset for predicting concrete strength. It stores key measurements for each sample, including cement amount, water amount, and curing time. These features will be used as inputs for the strength prediction model. This code stores two related lists in a dictionary, one for temperature measurements in Celsius and one for the matching concrete strength values in megapascals. Each position in the lists represents the same sample, keeping the features and target values aligned. This structure can then be converted into a data frame for analysis and modeling. A dictionary of data can be converted into a pandas data frame to organize it as rows and columns. Each dictionary key becomes a column, and its list of values fills that column's rows. This tabular structure makes the data easier to analyze and prepare for tasks such as choosing features and targets in machine learning. We choose the dataset columns that will be used as features or inputs for prediction. In this case, the features are cement amount, water amount, curing time, and temperature. These measurements are known before predicting the target value, which is the concrete strength. We separate the data into inputs and the outcome we want to predict. The target is concrete strength in megapascals, while the feature columns provide the input variables used for prediction. This split is essential for training a model because it clearly distinguishes the predictors from the desired result. Before analysis or modeling, check that the feature data and target data have the same number of samples, so every sample has a matching target value. Also confirm that the target values are complete, with no missing entries. These checks help ensure the dataset is consistent and ready to use. We begin by summarizing the dataset, its number of samples and features, the target column to predict, and the first sample's feature values. We also show that sample's strength value in megapascals. This frames the main engineering task, predicting strength from earlier measurements. This script creates a small concrete testing dataset with measurements such as cement, water, curing time, and temperature, along with concrete strength as the target value. It separates the input features from the target and prints basic information about their shapes and the first sample. The purpose is to show a simple engineering regression task, predicting concrete strength from earlier test measurements. Data quality risks. Missing data. Missing data can distort engineering analysis, even when only a few values are absent. In civil engineering, gaps such as missed traffic counts or missing corrosion ratings may change the patterns a model learns. This is especially risky when the missing values are tied to the conditions being studied, such as rainfall data lost during a storm, which could cause a drainage model to underestimate peak runoff. When data is missing, first consider why it is absent and whether the gaps could bias your analysis. Random gaps may be less harmful, but systematic gaps, such as sensors failing during extreme conditions, can make models look reliable in testing while performing poorly in practice. Always assess how missing data affects the trustworthiness of your model. Missing data should be handled with judgment, not by automatically deleting rows or filling gaps. Removing records can discard important cases, while using averages can hide real variation or problems in the data. A good analyst studies why values are missing, considers where the data came from, and documents any assumptions. Sometimes the missingness itself provides useful information for building more reliable engineering models. Python code missing data. Missing values can distort engineering conclusions, so data gaps should be checked before they are filled. Even small tables can reveal important data quality risks. The script begins by importing pandas for working with table-based data and Matplotlib's plotting tools for creating visualizations. These libraries prepare the code for data analysis and charting tasks. A small civil engineering dataset is created to study rainfall, runoff, and sensor conditions across sites A through F. It includes site labels, rainfall measurements, runoff measurements, and sensor status, with some rainfall and runoff values missing. This structure supports analysis of how missing data may relate to normal or storm conditions. A dictionary can be converted into a pandas data frame to organize its contents as a table. The dictionary keys become columns, and their lists provide the row values. This makes the data easier to analyze and manipulate using pandas. To find missing data in a pandas data frame, use the isNa method to mark each missing entry as true and all others as false. Then sum those true values by column to count how many missing values each column contains. This gives a quick overview of where missing data appears and how much of it is present. Filter the data to keep only records where the sensor status indicates storm conditions. Then count all missing values in that filtered subset by identifying missing entries and summing them across the data. This gives the total amount of missing data that occurs during storms. Filter the data to keep only records where the sensor status is OK, representing normal operating conditions. Then count all missing values in that filtered data by identifying empty cells and summing them into one total. This shows how many data gaps occur while the sensors are functioning normally. The code reminds us that rows represent sites and columns represent measurements, then summarizes missing values by column. It also compares data completeness by counting missing data points during storm conditions and normal conditions. Calculate the average rainfall across all sites while ignoring missing entries. Then use that average to fill gaps in the rainfall data. This makes the dataset more complete for analysis, but it can also reduce natural variation in the values. Compare the standard deviation of the original rainfall data with the standard deviation after missing values are filled using the average rainfall. This shows how mean imputation changes variability and may reduce evidence of extreme weather events. We compare the rainfall data's standard deviation before and after filling missing values with the average rainfall. This shows how mean filling can change the apparent spread of the data. The key caution is that replacing gaps with averages may hide the true variability of extreme storms, which can reduce accuracy in engineering models. Set the data by monitoring site and focus on rainfall and runoff measurements. Then identify missing values, convert those true or false results into ones and zeros, and plot them as a bar chart. The chart summarizes where measurements are missing across sites, with clear labels and adjusted spacing for readability. This script examines missing data in a small civil engineering dataset, showing that gaps are more common during storm conditions than normal conditions. It fills missing rainfall values with the column average, then compares variability before and after filling. The key lesson is that average-based filling can hide extreme storm behavior, so data gaps should be understood before they are corrected. Missing data. Missing data can seriously affect engineering analysis by changing how a dataset is interpreted. In civil engineering, gaps may come from sensor failures, missed measurements, incomplete tests, or power losses, creating uncertainty about the true condition of a system. If models ignore these gaps, they may learn from incomplete or biased information and produce misleading results. The effect of missing data depends on why it is missing. A few random gaps may be manageable, but missing values often occur during important conditions, such as extreme events or equipment failures. Because these gaps can reflect stress, human actions, or system breakdowns, treating them as random can cause models to underestimate risk or perform poorly when they matter most. When handling missing data, use engineering judgment instead of automatic fixes. Dropping incomplete rows can remove valuable information, and filling gaps with averages can hide real variation or create misleading patterns. First, examine where and why data is missing, and consider whether the missingness itself is meaningful. This leads to more reliable models and fewer errors from incomplete data. Python code, missing data. Missing values can conceal engineering risk, so data quality should be checked clearly and early. Small tables and simple summaries make problems easier to see and support careful judgment. The script begins by importing key Python libraries for data work. Pandas supports tabular data manipulation and analysis. NumPy handles numerical operations in arrays, and Matplotlib's plotting tools create visualizations. Together, these imports provide the basic setup for data handling, calculation, and plotting. We create a small bridge monitoring dataset organized as a dictionary. It records 6 hours of observations, including strain measurements, temperature readings, and whether storm conditions were present. Missing strain or temperature values are marked as not available, allowing us to examine whether gaps in the data are related to storm events. A dictionary can be converted into a pandas data frame to organize its contents as rows and columns. The dictionary keys become column names, and their lists provide the row values. This tabular structure makes the data easier to analyze, such as checking for missing values or filtering rows by conditions. This code counts missing values in each column of a data frame. It first marks which entries are missing, then totals those marks by column. The result shows how much data is missing for each feature, helping assess data quality before further analysis. To compare missing strain data in storm and normal conditions, filter the data into storm hours and non-storm hours. For each group, identify missing strain values and calculate their average to estimate the proportion missing. Comparing these proportions shows whether missing strain data is more common during storms. The data consists of hourly bridge monitoring samples, with columns describing measured features and their context. We check how many strain and temperature values are missing, then compare the rate of missing strain data during storm and normal conditions. The key takeaway is that missing data may be linked to critical conditions, which could reveal an important pattern or risk factor. This plot shows strain readings over time and highlights what data is missing during storm hours. Observed strain values are plotted against hour with circular markers, while missing readings are marked in red at a fixed strain level, so gaps are easy to identify. Axis labels, a title, a legend, and a light grid make the visualization clear and help assess the pattern of missing data. This script examines missing bridge monitoring data for strain and temperature during hourly readings. It finds that strain readings are missing more often during storm conditions than during normal conditions, suggesting the missing data may be linked to critical environmental events. A plot then highlights the missing strain values, helping show how data gaps align with storms and why environmental context matters in analysis. Outliers. Outliers are data points that differ sharply from the overall pattern and can reduce model quality if ignored. In civil engineering, they may come from real extreme events or from errors such as faulty sensors or incorrect data entry. Because outliers can strongly affect how a model learns patterns, they should always be investigated rather than automatically treated as wrong. Outliers can make models less reliable because they may try to learn from unusual or incorrect data as if it were normal. Errors such as a wrong rut depth, abnormal water flow from a burst pipe, or distorted images from glare or motion blur can skew training and lead to poor predictions. Identifying and addressing these anomalies helps models perform better in typical engineering conditions. Outlier analysis requires both statistical evidence and engineering judgment. Extreme values may be valid signals of real system behavior, or they may be errors that could distort a model. Before removing or keeping them, verify the data source, compare related measurements, consider system limits, and document the decision. This helps ensure reliable and safe data-driven engineering results. Python code. Outliers. Outliers can distort patterns in engineering data, so it is important to compare typical readings with suspicious ones. Small examples help make these risks easier to understand. We import pandas to organize and analyze strain readings in table form, and Matplotlib's plotting tools to visualize the data. Together, these libraries help us manage engineering data efficiently and spot possible outliers in the readings. We define bridge strain readings in microstrain, mostly near 120, with one much higher value of 480 that may be an outlier. We also assign each reading a sequential identifier, starting at 1, so the measurements can be tracked and used in later analysis or visualization. We organize the strain readings in a pandas data frame, with one column for sequential reading IDs and another for strain values in microstrain. An assertion then checks that the data frame has the same number of rows as the strain value list, confirming the data is complete and correctly structured. To find possible outliers in the strain data, we use the first and third quartiles to describe the lower and upper parts of the data. These values show where 25% and 75% of the data fall, and they are used to calculate the interquartile range. That range then helps set the boundaries for identifying outliers. The interquartile range is found by subtracting the first quartile from the third quartile, showing the spread of the middle half of the data. To flag unusually high values, add 1.5 times this range to the third quartile to set the upper outlier limit. To identify possible outliers, each strain reading is compared with the calculated upper limit. Readings above that threshold are marked as true in a new possible outlier column. The true values are then summed to count how many readings were flagged, and the result is stored as an integer for clarity. We calculate the average strain in two ways, first using all readings and then using only readings not flagged as possible outliers. Comparing these two averages shows how much the suspected outliers affect the overall strain measurement. The analysis summarizes 10 bridge strain readings and reports an upper outlier threshold to identify unusual values. It then shows how many readings exceed that limit and compares the average strain with and without those outliers to show their effect. Any detected outliers should be investigated, since they may indicate either a sensor fault or a real extreme load. The plot shows sensor readings as a scatter plot, with normal values in steel blue and possible outliers in crimson. An orange dashed horizontal line marks the outlier threshold, making it easier to see which readings stand out. The axes label the reading number and bridge strain in microstrain, and the title highlights how one unusual reading can influence engineering summaries. A legend and clean layout make the visualization easier to interpret. This script checks bridge strain readings for possible outliers using the interquartile range method. It sets an upper threshold based on the first and third quartiles, then flags one unusually high reading. By comparing the mean strain with and without that value, it shows how a single outlier can distort engineering results. The flagged reading should be investigated as either a sensor fault or a real extreme load, and the plot helps show its effect on the dataset. In this lecture, you learned to identify tabular, time series, and image-style data structures in civil engineering contexts. Explain how features, targets, rows, columns, and samples relate to engineering measurements. And recognize common data quality issues that can mislead models. In the next module, Module 2, we will go over engineering data tools. Thank you for your attention. See you all in the next lecture.